Next, let's briefly talk about the linear assumption. Remember that SVD is actually limited to linear projections, and it focuses only on a low-dimensional linear projection that preserves the Euclidean distances. Therefore, let's say that if the data point is actually concentrated on a spiral shape, then SVD will no longer work. Therefore, basically, we will need nonlinear methods to perform dimensionality reduction. And one of the most famous nonlinear dimensionality reduction methods is isomap. And the idea of isomap is quite simple. Let's say that we're given a bunch of points that looks like this in a three-dimensional space. And the first step of isomap is just to build an adjacency graph. And the way we build this adjacency graph is that for each point in this data set, we will just, for example, we can just select the k-nearest neighbors, and we can build an edge between this point and its k-nearest neighbors. And after we build up this graph, the distance between any 2 points would be just the graph distance. For example, if 2 points are 2 hops away, then the distance between these 2 points would be just 2. And after we build up this adjacency graph, we can compute the pairwise distance matrix, and then we can perform SVD or PCA on this pairwise distance matrix for dimensionality reduction. And another method of nonlinear dimensionality reduction is that we can use deep learning. And the simplest model of doing this is just a stacked autoencoder. It is no more than a simple feed-forward, fully connected neural network where the input will go through several layers of linear and nonlinear transformation to recover or reconstruct the input itself. And usually, the output of the middle layer, which is X2 here, will be used as the representation of the data. And this is the data of reduced dimensionality that we always want. And even more, we can have a slightly advanced version of stacked autoencoder, which is stacked denoising autoencoder. And in the stacked denoising autoencoder, instead of using the original input, we will first corrupt the input. Basically, we can randomly set some entries of the input to 0, and we call this the corrupt input. And we will feed this corrupted input into the neural network, and it will go through, again, several layers of linear and nonlinear transformation to recover the clean version of the input. And basically, this is the idea of stacked denoising autoencoder. As always, the output of the middle layer will be used as the representation of the data, or the data of the reduced dimensionality. And one nice thing about this stacked denoising autoencoder is that it can be easily extended to handle multiple types of data. For example, let's say that we have this word paper matrix where each column actually represents which word this paper contains. And besides this word paper matrix, we also have the paper's citation network. For example, if paper 1 cites paper B, then there will be an edge between paper 1 and paper B. And this is called a citation network. And the question is how to reduce the dimensionality of the paper here while taking into account the citation network. And the answer is that we can produce or develop a relational version of the stacked denoising autoencoder such that we can perform unsupervised representation learning or dimensionality reduction. And we can also enhance the representation power of these representations with relational information. And the basic idea is that while we are performing dimensionality reduction, we will also impose an additional constraint that if 2 papers has an edge between them, we will constrain them so that that representation would also be close to each other. For example, the easiest way would be just to add a L2 loss between each pair of the representations. And this is just a brief and very high level idea, and we will talk about this more later in the semester in other topics.